Okay, so chemistry is actually the study of matter, okay? And that's what it breaks up. That's like its title. So biology is the study of life, chemistry is the study of matter. And so what we're going to talk about is what exactly is matter. How do we classify it? Because scientists love to classify things. Matter is anything that has mass and takes up space. Okay, so energy doesn't count. Light doesn't count. But anything that has mass and takes up space is matter. So a table, a glass of water, air. Okay, those are good examples of different kinds of matter. Anything that has mass and takes up space. Now, you may not think air has a lot of mass, but actually it really does. It's just not, compared to, say, a table, it's not as significant. It's not as dense. So, there's two ways to describe matter. It's either an extensive property or an intensive property. An extensive property is something that changes based on the amount of the matter in that sample. So, for example, if I have a glass of water, it has a certain volume, 8 ounces, 8 fluid ounces. Or if I have a 2-liter bottle of soda, it's 2 liters. If I have a bigger amount of matter in the sample, let's say I'm talking about a lake, that's a bigger amount. That's an extensive property. Volume is an extensive property. It depends on how much you have. Mass is a good example. If I have 1 chair, it might weigh 3 kilograms. If I have 30 chairs, it weighs 90 kilograms. So mass changes depending on the amount of matter you have. Okay, mass and volume are good examples of that. Intensive is a property that changes based on the type of the matter in the sample, not the amount. For example, density is a great example. Density of water is 1. It doesn't matter if I have a glass of water or if I have a lake of water. The density of water is 1. It doesn't change, 1 gram per milliliter, based on what's in there. Now, the density of gold is 19.3 grams per milliliter. So that means it changes on the amount, the type of matter, gold versus water, but not how much you have. Okay, boiling point, density, good examples of that. Okay, so there's 3 states of matter. There's a solid, a liquid, and a gas. A solid has a definite shape and a volume. It's not fluid, okay? So it's a chunk of matter, okay? It has a definite shape and a definite volume, and if you pour it, it just rolls. It doesn't flow. It's not a fluid substance. Liquids have an indefinite shape. They take the shape of their container, whatever it is. You take a glass of water and you put it in a vase, it has a different shape. You put it in a bowl, it has a different shape. And it is fluid, that means it flows. But it does have a definite volume. The volume doesn't change. If I put it in a glass and it's 100 milliliters, and I put it in a bowl, it's 100 milliliters. If I put it in a vase, it's 100 milliliters. So it has a definite volume. Gases, on the other hand, have an indefinite shape. So they take the shape of their container as well, and they actually expand to fill their container completely because their volume changes. They'll expand to fill it, whatever it is. So if I take a gas and I put it in a, a Tupperware bowl, a small Tupperware bowl, it'll fill that bowl up completely as long as it has a lid on it. Then if I take that same amount of gas and I put it in a bigger bowl with a lid on it, it will expand to fill that container. So it doesn't have a definite volume. The volume changes, and it doesn't have a definite shape. Okay, and it's easily compressible. That means you can squish it. Okay, and it is also fluid. So these are some pictures of what they look like. Now let's talk about how matter can be broken down. It can be broken down either into pure substances or mixtures. A pure substance has only one kind of substance present. In other words, it's not mixed with anything else. It can be either an element or a compound. We'll talk about that in a minute. Iron is an example. Okay, if I have pure iron, not the stuff that you put in your car or whatever, that's got stuff mixed in with it. Pure iron is an element. Pure distilled water is a compound. It's also a pure substance. Not tap water. Tap water's got stuff dissolved in it. Fluoride being the obvious one. Oxygen. Okay, if you have an oxygen tank, that's pure oxygen. Air is not pure oxygen. Air is actually a very low amount of oxygen. Mixtures have more than one kind of substance present. Actually, the vast majority of the stuff you guys are going to deal with are mixtures. They can either be homogeneous, and the word we're going to use for that is we're going to try and call them solutions, or heterogeneous mixtures. So salt water is a mixture. It's got salt and water. Italian salad dressing, if you've never seen it, it's got oil, it's got vinegar, and it's got spices in it. Air is a mixture of nitrogen, oxygen, and carbon dioxide. So it is a mixture. And amongst other things, there's other things. So within pure substances, elements have only one kind of atom present. When you're looking at the symbols, there's only one capital letter. That's how you know. Even if it's got a number, as long as there's only one capital letter, it's an element. That's how you know. Capital letters define elements. Compounds have more than one kind of atom present in a whole number ratio. So you're going to see numbers again. But see how there's more than one capital letter? Okay. So that's what you're looking for, is how many capital letters. 2 or more capitals equals a compound. My abbreviation is CPD. They're both examples of pure substances. They got nothing else mixed in. So each element symbol begins with a capital letter, and when you guys are writing these, I expect you to do it that way. I don't want to see FE, okay? Even if you write in all caps, you need to make a habit of doing FE. The number of capital letters tells you how many elements are present. A mixture is a blend of 2 or more components, 2 or more things mixed together. Heterogeneous is when you can see the chunks. You can see the parts. Okay, chicken noodle soup, you've got noodles, you might have chicken, you might have potatoes, and then you've got the broth. Concrete, you can see the concrete, but it's mixed in with rocks and stones, things like that. Gravel is a good example. Chocolate chip cookies are a good example. Anything where you can see the parts that are made out of. Homogeneous, and we're going to call these solutions, are mixtures in which the composition is uniform throughout. You can't see the other stuff, okay? It's uniform, I guess. You can't see the parts, even though we know they're there. So olive oil is a mixture of a bunch of different kinds of oils. Vinegar is actually water, and then this guy is called acetic acid. Salt water has got NaCl and H2O. Kool-Aid has got sugar, coloring, preservatives, water, and a little bit of flavoring. Okay, so they're mixtures, but if you make up some Kool-Aid, you're not going to see, oh yeah, look, there goes the sugar, and oh, there goes my food coloring. No, it doesn't work like that. You can't see the individual parts. Okay, so identify either the following as either solutions or heterogeneous mixtures. So food coloring is actually a solution. It's got a bunch of stuff mixed in, and it's got water in it. Ice cubes and liquid water is a mixture. Okay, I'm going to use an M for that one, because you can see the different parts. Mouthwash is actually a solution. If you look on the back and you see the ingredients and there's more than one, makes it a solution. Mashed unpeeled potatoes means you can see the potato peel. This is a mixture. Hot tea is tea, but if you take the tea bag out, you can't see the individual parts, so this is a solution. And then if you have a stream with gravel on the bottom, that is a mixture. So it's kind of, you kind of have to get a feel for how these work. Air is a mixture. It is not a pure substance. Or sorry, not mixture. It's a solution. It is not a mixture. And it is not a pure substance. It's got a bunch of stuff in it, but you can't look at the air and go, oh yeah, look, there's carbon dioxide, and there's an oxygen, and there's a helium. It doesn't work like that. Okay, you can't see the individual parts, so it is a solution, and it's the best example of a gas solution that I know. Okay, physical properties and changes. Physical properties describe the characteristic of a substance. You look at it and you make a measurement on it. That's literally what it is. Is it blue? It has a density of 1.0. It boils at 95 degrees Celsius. It's a liquid at room temperature. Whatever the description is, it is physical description of it. Okay, a physical change is the properties of it change, but the chemical composition does not. So if I cut hair, I'm just making it shorter. I'm decreasing its mass. So you're changing some of the properties, but you're not changing the chemical composition. Okay, if you crack an egg, it doesn't change it from being an egg. It turn it into bread or something. And if you cut copper wire, all you're doing is changing the mass. Chemical properties, on the other hand, describe how it reacts with another substance, and that's really the key word. You're going to see the words reacts with, or you'll see words like burn, rot, rust, decompose, explode. These are the usually exciting things. So, in a chemical change, it's a change in which the chemical composition of the substance changes. So, if you took that egg that you cracked and you put it in a frying pan and you started cooking it, that is a chemical change. The cracking process doesn't change it, but the dumping it in the frying pan changes it. Okay. Biggest thing you want to look for in a chemical change is if you see a temperature change, other than when you provide heat. So if I'm boiling water, that doesn't count. I'm adding heat. That doesn't count as a chemical change. But if it's just sitting there and all of a sudden I drop something in there and they're both the same temperature and it jumps up in temperature, it drops way down in temperature, that is a chemical change. If it changes color, and again, if I take clear water and I put blue food coloring in it, it's not a chemical change. It's changing color, but I put something blue in it. Okay, so think about it a little bit logically. Producing a gas, and again, boiling doesn't count with this. And if it produces a solid, same thing. Freezing doesn't count. So if I bleach clothes, the biggest thing you want to look for is, can I get it back? Can I turn it back to what it was? That's kind of the idea. So if I bleach clothes, you know, I drop some bleach on my blue jeans, they're not going back to blue jeans. Okay? They're going to be bleached, and that's a chemical change. It's not going to go back. If I take nail polish off with acetone, okay, I'm removing that. It's not like if I rub it back on there, it's going to go back on my nails. It's not going to work like that. So it's anything that you can't get back to the original way. So classifying as chemical, physical. Boiling, like I said, physical. Diamond cutting, okay, that's physical. Sugar dissolving, also physical. I know it looks like it's not, but it is. Dissolving and boiling are the ones that throw people off the most. Vinegar reacts with, see that word? That means chemical. Yeast reacts with, that's chemical. Okay, it's changing it from yeast and sugar to form carbon dioxide and alcohol. Aluminum has a low density, that is physical. It's a description. Iron rusts, chemical. Come on. Steam condenses, okay, that's the reverse of boiling, that is physical. Okay, and then I'm going to do some demos in class, so I'm going to pause the movie right here, but the idea is when you're going to go through it, you're going to look at these demos that I'm going to do and identify whether or not they are chemical or physical